We ready to get going? Yep, okay. Well, thank you very much for everyone for coming along to the closing keynote. Actually, that'll be next year, but yeah, thank you for coming along. There's still time to go and see John Skeet if you want to. If you want to duck out now, I won't be offended. That's totally fine. So I put out a Twitter poll a few months before this and said, hey, you know, what do people want to hear about Elasticsearch? And it was a unanimous decision. They want to hear about using Elasticsearch with .NET. So that's what this talk is going to be about. So just to kind of run through a few of the things that we're gonna look at today. This is going to be a very, very example-heavy talk. So I'm going to be switching between slides and examples. I like to see code myself, so there's going to be plenty of code here for you to see. So we're going to start off basically with what Elasticsearch is, how that fits into the great scheme of the things in the Elastic Stack. And then we're going to get up and running with the .NET clients. So there are 2 clients, and we'll go into that in a little bit. And we'll take a slight detour to just kind of go over mappings and analysis. We need to kind of do that because in order to talk about queries and aggregations, we kind of need to just kind of dive into that a little bit. And then we're going to finish off with completion and recommendations. So those queries and aggregations we're going to look at a few different things there, buckets, pipeline aggregations. So for this particular talk here, I'm using a few different data sets. One of them is the Stack Overflow data set. I've taken the entire history of Stack Overflow, questions, answers, users, their badges, and I've indexed that into Elasticsearch running on my old trusty laptop here. So if it holds up, hopefully we'll see some interesting insights. So they say that every good talk should start off with a pithy quote. So I scoured the internet. I found this guy saying something about Elasticsearch, enabling you to find the answers to questions you don't yet know you have. And I think that kind of sums up Elasticsearch quite well. You have all these reams of data coming in. You have no idea what you want to do with it right now, but for the moment, you're just gathering all of that data up, shoving it into Elasticsearch. And then at some point, someone asks you, hey, this server goes down, or someone's attacking the server over here, and you're aggregating all of those logs into Elasticsearch. You can then start going and exploring those particular pieces of information and try and piece together a puzzle of exactly what is happening there. So what is Elasticsearch? This is the very high-level view. So it's a distributed and scalable search and analytics engine. It's schemaless, although we'll see that that's actually an implied schema from what you send it. But we'll talk a little bit about that in mappings. You interact with it with the JSON REST API. And there are client libraries for pretty much every programming language you can think of. And so Elasticsearch itself is open source. It's under the Apache license. It's built on top of Lucene, which itself is also under Apache license. So it allows you to perform real-time, near real-time search on large amounts of data, full text search as well, search relevancy, scoring, aggregations, geospatial. It also handles multiple different languages. And there are plugins for handling non-English languages as well. It's highly available, so you can run Elasticsearch on a single node. You can run it on a bunch of nodes. And those can be separate machines. They can be the same machine. And Elasticsearch will largely handle the scaling out of that for you. So if you find that you're reaching the limits of your particular cluster, you can add another node. And Elasticsearch will balance the shards of an index across those other nodes. So Elasticsearch, that's probably all I'm going to say about Elasticsearch, because we could talk for hours and hours about that. But Elasticsearch itself is part of something known as the ELK-B stack. So those of you who are familiar with Elasticsearch, the ELK stack is something that's very popular within the logging world. So using Elasticsearch, Logstash, and Kibana. So using Logstash to bring logs into Elasticsearch, then using Kibana as a visualization. And about a year and a half ago, we also brought on top beats as well. So then we were kind of thinking, well, how does the B fit into ELK? You know, is it ELK-B? Is it Bleck? Is it Kleb? So we came up with ELK-B, but we didn't really. It's actually the Elastic Stack. So Elastic Stack comprises of Kibana, which is the user interface. So if you've come and visited the booth, you've probably seen the nice, pretty visuals there of various different data sets that we've had. Elasticsearch there is the actual search analytics engine where all of the data is stored and is searched. Then Logstash and Beats are the ingest to actually get data into Elasticsearch. On the side there, XPack are a bunch of additional commercial plugins that Elastic offers that provide additional functionality to Elasticsearch. And then finally, Elastic Cloud is our Elasticsearch as a service offering. So we take care of managing the cluster for you. If you want to scale it up, we take care of that, scaling it down, et cetera, et cetera. Multiple use cases, people using it for log analysis, so Verizon, NASA using it for analytics of the Mars rover telemetry data. GitHub uses it for search. So if you've ever searched for anything on GitHub, that's going to be hitting an Elasticsearch cluster. So that's enough preamble. Let's get started with .NET. So the .NET side of things, there are essentially two clients. There's Elasticsearch.NET, which is the low-level client. So that's a very unopinionated, dependency-free client there. It has the entire Elasticsearch API mapped. It works basically with strings, objects, list of strings, list of objects, and byte arrays. Very unopinionated. That's the low level. And then on top of Elasticsearch.NET, you have Nest, which is the higher level client. So all the request types, all the response types are mapped to strongly typed C# types for you to work with. It uses JSON.NET under the covers for JSON serialization, and it exposes and actually uses Elasticsearch.NET under the covers. So you can still use the low-level client if you're using Nest simply by calling client.lowlevel. You have access to the low-level client. Some of the nice things about Nest, though, that it has on top of Elasticsearch.NET, and why I personally think it's a better choice to get started with, is it provides you with additional functionality, things like covariant result set. So for example, in Elasticsearch, when you index data, you index a JSON document. That document goes into an index in Elasticsearch, and that document is going to be of a particular type as well. You can specify a type for that document. And you may have more than one type in one index. So for example, in the case of Stack Overflow, you might have a question, Stack Overflow question, and then you have a collection of answers, and those are a collection of answers for a particular question. So you may have questions and answers both indexed into the same index, and you want to return questions and answers. That's what covariant results sets will be able to give you, and Nest handles that, and we will deserialize into the correct type. Also has some functionality for providing auto mapping. So given a POCO, given a C# type, it can infer the correct mapping to send to Elasticsearch there, and provides some nice other functionality there with operator overloading. For example, if you need to combine form a compound query from two different queries, there's some overloading there that allow you to do that. We'll look at examples of all of these. So let's get started. So this is how we would end up connecting to Elasticsearch with the low-level client. Simply new up a client. And this client here is going to be trying to talk to Elasticsearch on localhost on port 9200. So that's simple. Now, sometimes we want to provide additional settings as well to the client. So specify a different URI for a start. Maybe we want to use a different type of connection pool. So for example, Elasticsearch may be running on a bunch of nodes. They all have a different address to them. We may want to use all of those addresses and pass them to the settings there so that when a request comes in, the client is able to send it to any one of those nodes. So same as before, we can run that, and we have a client. So the client here, and so similarly with Nest, we can new up a new client, and we can see here that we have the low-level client here available as a property on the Nest client. So a little bit more of a complicated example here. So this is using some of the additional Nest features that I was talking about. So we have a bunch of URIs here. So we have a 3-node cluster here running on 9200, 9201, 9202. We pass those to a sniffing connection pool. So we have a bunch of different connection pool types. sniffing connection pool is quite good for clusters that automatically scale, because that sniffing connection pool is able to send a sniff request to Elasticsearch, understand if new nodes have been added to the cluster or if nodes have dropped out of the cluster, and then use those in order to send requests to the correct place there. In addition to the connection pool, we have a set of connection settings here where we can specify a default index for Elasticsearch for the client to use if an index hasn't been specified on the request. We can also specify an index here for a particular type as well. So any time that we're going to perform a search on users, posts, questions, answers, use this particular index. And we can pass in a collection of indices there as well. If, for example, we had our data across multiple indices, we could pass in a comma-separated string of indices to use there. Obviously, this is all overridable on an individual request basis. These are just defaults that we can run with. So let's make our first request with the low-level client. So we're just going to perform a search here, a simple search on the posts index with a question document type. And we're just going to perform a query here. So we specified our query here with an anonymous type. This is going to be serialized into the JSON query DSL that you've probably seen on the site. And we're simply doing a match phrase query here. This should never happen. And we're just going to take the response of that. So the generic string type here on the search call is the response type that we expect to get back. So if we run this one, we have a massive blob of JSON come back, which isn't very easy to read like this. So what we're going to do is we're going to run this example again. But now what we're going to do instead, so we have the same query as before, but what we're going to do instead is we're going to take advantage of some of the connection settings. So what we're going to do here is we're going to disable direct streaming. So we're going to buffer the request bytes, and we're going to buffer the response bytes. And then when that request is actually completed, we're going to log out the request and the response to the console, just so we can see what's going on. So for all of these examples, that's what I'm going to do, so we can get an idea and understanding of what's being sent to Elasticsearch and what's coming back. So if we run that same query again, we can see it's a little bit easier to read now. So this is the query that we sent in, match phrase, this should never happen. So we have a 200 response back. It took 61 milliseconds. And inside of here, inside of source, we should have a collection of, inside of hits here, we have a collection of the documents within Elasticsearch that were a match for our particular query. So in each one of these documents, this source property here contains the original JSON document that I sent in. So we can see there's a few different properties here. Last edit date, the title of the question. So what's your should never happen exception? The creation date, the body, which we can see as HTML here. So we were searching in the body for this should never happen. So we should see that somewhere. Yep, should never happen inside of the body. And we can just see that we've returned back the first 10 records there. And in total, there's 521 questions in Stack Overflow that have this should never happen in the body. So that was all with the low-level client. We're now going to start looking at the high-level client, and the rest of the examples here are going to be working with that high-level client. So I've done a similar thing as before. I've disabled direct streaming, so we capture the request and response bytes. And again, I'm just going to be logging those out to the console. So down here, we can see we're going to perform a search request specifying our question type, performing a match phrase query. Same query as before, we're just using the Nest query DSL here instead. And this query DSL is based around Lambda expressions. So we can see here, we can specify a query, match phrase query. We want to run it on the body field. And this is our particular query text. And you can, what you'll be able to see here when I run this query is that the layer of this Lambda API is very, very similar to the layer of the JSON query DSL that actually ends up getting sent to Elasticsearch. So if you're ever looking at examples with the JSON query DSL and you're trying to translate that into what it looks like with Nest, you can almost picture what they're gonna end up looking like. And we can see again that we have results back here. Interestingly, for these connection settings here, I've performed a search on questions, but the actual URL that has ended up being hit here is the localhost just to search. So what I've ended up doing here is actually searching across all indices and all types in all indices. And that's because I didn't specify a default index to use. I specified a type here, which was the question type, but I didn't specify an index. So if I was to add in an index now, and say to use the posts index, and run that one again, we can see now we're just looking at the posts index in Elasticsearch, and we're only looking at question types. For those of you that are less comfortable with using the Lambda API, there's also an object initializer API as well. So you can initialize a search request object here. Same as before, same as using the Lambda API, except you can work with objects here and pass your search request object in. The results of this will be the same as we saw before. Okay, so we've kind of looked at the first kind of searches. Obviously, Elasticsearch can do more than just search. We actually need to get the data into there first of all. So running through this particular example, we're going to create an index. We're going to specify one shard for that index. So an index can be split up into n number of shards, where each shard itself is a leucine index. So we're just going to specify one shard for our Elasticsearch index here. We don't need any replicas. We're only running on my machine. I don't need to replicate the shard to other machines. So we're simply going to run with one shard here. I'm going to map my conference type here that I've specified. And just going to new up a new conference. So for here, and I'm just going to index that into Elasticsearch. So if I run that one, we see this put request here. So I've created the documents index with a bunch of settings for which to use to create that, specified my mapping, which we'll look at in a sec. And then I've just posted a document to there. And I've received a 201 back there to say the document has been created. So your typical HTTP response codes you'll get back for created, OK, bad request, et cetera, et cetera. Now, of course, if we're indexing many, many documents, we don't want to be inserting those documents one at a time. So we can also create a couple of documents and index those both at the same time. Now, what index many actually ends up doing, it uses the bulk API behind the scenes. So there's a bulk API for performing a bulk of operations, a bunch of creation operations, deletions, updates, etc. So index many is just a really nice shorthand for using the bulk API. So we can see here that this has ended up calling the bulk endpoint, our two documents there that we have indexed. And we can see that we have a 201 response back for each one of these documents. The order of these items that come back are the same ordering as you saw, the order in which we sent the bulk operations to them. So we should see this one would be the Oslo Spectrum Norway location, and this one here would be the Hilton Sydney. And as I mentioned, index many is really just a shorthand for the bulk API. So the bulk API here, what we just saw is exactly the same as doing this here. So calling the bulk API, calling create many, passing it our collection of conferences, and indexing those into Elasticsearch. So we can index documents. We can also update them, obviously. So if I create a conference object here, index it, pull that document back, and then go and update it. So here we go. I put my conference object in. I then pulled it out. I then changed the end date. So then change the end date of the conference, because we all want it to finish tomorrow. And then I've just updated that conference document there. What I've also done here, Elasticsearch has a concept of optimistic concurrency control. So when I pulled that document back from Elasticsearch here, I also got a version number back as well. So the version of that document as it exists in Elasticsearch, so that when I've gone and done my update now, so I've deserialized that. I have a conference object now in my application. When I go to make the update, it's possible that someone else has modified that document in between. So I can also send the version number back that I received when I originally fetched the document. I can send that back and update the document. So if the document has changed and the version number's changed, I would get a 409 conflict back to say, hey, this document has actually changed in between you fetching it and you updating it. So we don't actually have to grab the document back each time. We can just perform an update instead by sending just a partial document to Elasticsearch. So again, create a conference, but now I can just use an anonymous type that has the same property name as the end date here on my conference. I can send that to Elasticsearch, specifying the ID of the document that I want to update, and let Elasticsearch perform the update on Elasticsearch itself. So we just have a quick look at what the JSON ends up looking like for that. Create my conference, get a 201 response back. And then I just post my document just purely with the end date that I want to change. So receive a 200 back there. And then I finally fetch the document here just to prove that that end date has actually been changed, which we can see here. So partial update's good for when you just want to modify things without actually going fetching documents. And similarly, we can also delete individual documents as well. We can also delete many documents. In older versions of Elasticsearch, there was a delete many API that allowed you to specify a query for a bunch of documents that you wanted to delete. And in newer versions of Elasticsearch, there's a task-based API for performing that deletion as well. So that was kind of a brief rundown of all of the CRUD operations and a brief look at some searches. So you have a JSON blob that you send into Elasticsearch. You've indexed that document. Now what actually happens? So you can see I've represented Elasticsearch cluster there as a gray thundercloud there to represent the speed at which it operates, lightning fast. So we now need to look at mappings. So we've indexed a document. What is actually going to happen? So by default, Elasticsearch is, as I said before, is schemaless. But when you send a JSON document to Elasticsearch, it's going to, by default, first of all, if you send it to an index that doesn't yet exist, it will create the index for you. And then what it will also do is it will infer the mapping for the document that you've sent to it based on the properties of that document. So for example, if it sees ISO 8601 strings, it will expect those to be date times. If it sees integers, it will map those as integers, so on and so forth, for all the primitive types you can imagine. Where it sees an object property, it will map that as an object type, so you can have nested objects within your JSON document. So in this particular example here, this is my Stack Overflow user with a bunch of different properties, ID, reputation, profile, age, and they have a collection of badges. So these are the badges for questions that they've answered. They've received a badge for, the date which they've received that, whether it's a gold, silver, or bronze badge, and a name for the badge as well. So the name for the badge is usually the language which they've received this badge for, so C#, F#, etc. So within Nest, we have, when you want to map a particular strong type, so those default mappings are usually good for when you want to get up and running, but for most scenarios, you actually want to control the mapping for your documents. The reason you want to do that is there are domains in which you operate. You know more about your data than Elasticsearch does. So for example, in the Stack Overflow questions, the body of each question is HTML. There's a bunch of HTML tags in there. Do we want to be, when we search, do we want to be searching with HTML tags in there? No, we don't. But by default, what Elasticsearch will do would just map that using a standard analyzer, and we'll end up indexing a bunch of HTML tags as well, which is what we don't want to do. So we look at mapping our user type here. We're going to specify that it's going to go into the user's index. And we're just going to say to the client, look at this user type here. Look at all of the properties on it. And tell Elasticsearch which properties to use for the mapping for this user type. So if we run this one, we can see here that the properties here are, the ID of a user is an integer, reputation is come through as an integer, date time offset, a date, so on and so forth. It's mapped badges here as an object type, and it's also recursed down there and seen that each badge type also has a string, an integer, and a date as well for the name, class, and date. So auto mapping's great, that gets us going, but we might want a bit more control than that. And that's where properties come in. So we can auto map to say to the client, infer the types that you need to send to Elasticsearch for our user type, but now I actually want to override the client's inferred types. So I want to map age here as a byte in Elasticsearch because I don't want it taking up an integer's worth of space. No one's going to be older than 255. So I'm just going to map age as a type. I still want to work with it as an integer or as a nullable integer as it is in my application, but I want to map it as a byte in Elasticsearch. And I also want to map badges as a nested type as well. I don't want them to be object types. I want them to be nested types. So I can also say auto map badges as well, and then I want to override the properties there. And whenever you see the class, a gold, silver, bronze badge, I want you to not only analyze the actual text that comes in for that class badge, the silver, gold, bronze, I also want you to just store it verbatim as well. I want you to store also what comes in, and I want you to store that in a field that's going to end up being called class.rule. So I'm actually mapping the class property of a badge here in two different ways. I'm having it analyzed because I may want to perform some searches on it, which we'll have a look at in a second. And I also want to store it verbatim as well so that I can aggregate on it and see the original values. So if we have a look at this one here, and we look at our user type here, and we have a look at our badge types. So badges has been mapped as a nested type. Our class type here has a type of string, so it's going to be analyzed. But then it also has this fields object here as well, with a rule field, a rule multi-field as they're called, multi-field as they're called underneath as well, which is a not analyzed field. Another way that we can map as well, so we can auto map, we can override the mappings using properties. We can also pass a visitor in as well. So say, for example, we wanted to map all of our string properties on our user, and we also wanted to set up a rule mapping there. We wanted to store verbatim the original text for all of the string properties of a user. We can use the visitor pattern to do that as well. So we can use our not analyzed visitor here. We can specify a rule field. specify it as being not analyzed, and we can pass our visitor then into the automap function. So that's going to, as it's going through and inferring all the string fields of our user, it's also going to map each one as a raw field as well. So if we just run that one, we can see here that display name, yeah, it's come through. All of the string fields also have a raw not analyzed field as well. So that was a brief detour in mapping. So we've indexed, we've looked at how we want to map our JSON documents. Now we need to have a look at exactly how individual fields there on our documents are going to be analyzed. And this is really kind of, if there's nothing else you take away from this talk, this is probably the one thing that's worth knowing. When you index a string field into Elasticsearch, it undergoes analysis by default. And the analysis that it undergoes follows this kind of analysis chain. It uses an analyzer, and an analyzer is made up of 0 or more character filters, a tokenizer, and 0 or more token filters. So what character filters do, first of all, they will pre-process that string. Maybe we want to strip HTML characters. Maybe we want to replace C++ with symbols with C++'s words. Then it's going to go to the tokenizer. The tokenizer is going to take that entire text and split it into tokens. And then the token filters are going to do additional things on top of those tokens. So they may remove tokens that we don't want there. So stop words, for example, the, etc. Maybe they provide synonyms for words there as well. Maybe they do a bunch of different things as well. So the standard analyzer is the one, as I said, that normally gets applied to string fields. So it has no character filters, but the tokenizer that it uses Unicode text segmentation to break down that string of characters into words, into tokens. And then it runs it through a bunch of token filters here. So it lowercases it removes stop words. So if we were to look at basically how that happens, if someone makes the claim F# is clearly the superior language, then running that through the standard tokenizer, we're going to get split up into these tokens by the standard tokenizer. So we can see that the sharp symbol is being removed, so have the stars. And as that's passed through the standard token filter, which is a placeholder, doesn't do anything right now. So that gets passed through exactly as it came from the standard tokenizer, then gets lowercased, and then stop words get removed. In this particular case, in the normal standard analyzer configuration, no stop words actually get removed there. And then what happens to all of those tokens? They go into the inverted index. So the original field from which these tokens came from, title, and then we have lexicographically sorted the individual tokens from that analysis stored in the inverted index, and then the ID from which that token originally came from, the document ID from which that token originally came from. We can see someone else has made the claim here for JavaScript being the superior language as well. So let's have a brief look at how analyzers work. So I've got a very, very contrived example here for us to have a look at. I have my type here, a semantic version type, has an ID, has a version string, so semantic version string. So are we all familiar with semantic versions? Yep, so what we're going to do is we're going to specify a bunch of token filters. And what these token filters are basically going to do, because semantic version numbers, they're effectively strings. We have maybe 3 or 4 elements there, a major, minor, patch, maybe a build, maybe then a pre-release suffix as well. What we want to do is we want to take that, but we want to pad out each of the major, minor, build such that, for example, semantic version 11 comes after semantic version 2. So if we're just looking at these lexicographically, we would find that 11 would end up appearing before 2. So with this analyzer here, we're just specifying a bunch of token filters that are going to pad out each each number there, and then also preserve that pre-release suffix as well. So we have a bunch of token filters to do that are going to pad out the various sections. And then we have a token filter at the end that's going to then de-pad all of those filters. And we've put all of those together under an analyzer, a custom analyzer that we have here called semantic version. Tokenizer we're going to use as the keyword one, which is basically just going to take the entire semantic version string as it is and just pass it to the token filters. And then we've just provided some mapping for a semantic version here. So if we run this one, we've created our index with our custom analyzer. Then we want to check to make sure that our analyzer is actually doing what we think it should be doing. So we can use the Analyze API here to do it. So we have a 1.20 here. We have 1.149.0 alpha 3. So yeah, they still haven't released their version. So we're just going to run those through, specifying our semantic version analyzer we just set up, and see what we get back there. So we can see this is the token that's going to get generated for the first one. So it's nicely padded out 1, 2, et cetera, et cetera. It's also appended these Zs on the end because this isn't a pre-release, and we want the actual releases to appear after any pre-releases. And we can see that similarly that we also have this token is padded out here as well. So our analyzer seems to be doing what we think it should be doing. But we can run a little test on that as well. So we can index all of the semantic versions from 000 alpha 1 all the way up to 1919. So let's index all of those. So we've indexed those. And now let's run a term range query on our semantic version index. So we want to be looking for numbers between 120 alpha or 120A and 121. So what we see, we get back here is 120 alpha 1, alpha 2, alpha 3, et cetera, et cetera. And we're just sorting on the key here, the actual token, which would end up being the tokenized, the analyzed key from that. Interesting to point out here, term range query itself. So some queries undergo analysis, some queries don't analyze the input to the query. The term range query here doesn't perform any analysis on the input to the query. So what we're doing here is we're cheating a little bit. We're actually expanding these tokens out as well in a similar way to which our analyzer works, so that we can search on those ranges in a sensible way. And then we can have a look also then as well to see, well, I expected this document to match, and I didn't expect this document to match. You know, what's going on there? So we can ask Elasticsearch to say, hey, why did this one match? Why did this one not match? So given the ID of semantic version 4000, one of 8000, and this particular query, tell me whether it matches or not. So we can see for the first one, yes, within the explanation, we can see a description here that it did match because it was in this version range. And if we look at the second one, we can see there was a failure to meet condition. So 8000 didn't, the semantic version with ID 8000 wasn't within this range. And we can have a little look and see why that might be the case. So, yep, this semantic version is at 220 alpha 1. So it wasn't within the range that we were specifying in our query. So let's have a brief look at queries. Okay, so we're not going to be looking for Lionel this time, but we're going to be looking at some Stack Overflow data. So I touched briefly on queries and filters. Queries essentially fall into two kind of buckets. You have structured queries. So does this particular value fall within this range? Does it match this particular value? Does it match this regex? Does it match this particular prefix? And then you have unstructured full text queries. These are more kind of a blended, more of a fuzzy kind of query. So tell me stuff, give it a score to tell me how relevant this thing is to my particular query. And that uses things such as TF-IDF, BM25. They're two different types of similarity algorithms to determine a score for a particular document. And let's have a look at a few different queries. So again, we're just indexing our conferences, the ones that we saw before, one for Oslo, one for here. And then we're just going to perform a query on those. And we're just going to look for those that contain Spectrum or Sydney, match for Spectrum or Sydney. So we can see we got a match for both of them. But we can see here, though, that the Hilton Sydney document was actually scored higher than our Oslo Spectrum Norway document whilst looking at the location field. Does anyone know why that might be the case? Okay, so so it comes down to something called norms, which is based essentially on the length of that individual field. So Oslo Spectrum Norway having 3 words and being a longer field than Hilton Sydney. Hilton Sydney has ended up being scored higher than Oslo Spectrum Norway. So what we can do is we could look at just disabling norms for that particular field when we index it. So we can go and have a look at using a norms disabled visitor. So when it visits any particular string query, let's disable norms for that field when we actually construct the mapping for that type. And let's perform the same query again. And we can see now that we get the same score out now for Hilton Sydney and for Oslo Spectrum Norway. So we can also perform a term query here. So let's index those same 2 documents again, have a look for Sydney. But we don't get a match. What's gone on? Why is that? So if we have a look back to the analysis, it's because this location field has been analyzed, and it's been analyzed with the standard analyzer. So it's been lowercased. So as it's gone through analyzer, it's been tokenized, and then it's been lowercased. So a term query here doesn't perform any analysis on the input to the query. So we specified uppercase Sydney here. We don't find a match. If we specify lowercase Sydney, we should expect to find a match, which we do. So we get our Hilton Sydney document back. We can also use the verbatim rule field that we also set up here as well. So using location suffix rule, so we can still strong type against the location field here, but then specify to use the rule field that we set up earlier. And then we can use the original value that we actually provided here. So we would expect to see a match here for Hilton Sydney as well, which we do. So then we can also combine queries together here. So two match queries here, one for Sydney, one for Spectrum, and we've put those inside of a Boolean query and a should query here, so either or. And then we've also applied a filter here as well. So filter is not going to influence the scoring, but it's just going to filter on those that have a name that contains NDC. And we're also now going to boost anything that contains Spectrum. We're going to give that a boost of 2. So we would expect to see those appear higher up than those from Sydney. Yep, so we see our Oslo Spectrum Norway appear first. And as I mentioned earlier, we actually have a shorthand for this. So Boolean queries, compound queries are a very common case. So within Nest, we have a way of actually shortcutting that, so with operator overloading. So here we can specify the same query again. We can OR these 2 queries together, and then we can AND this filter query here. So using the unary plus there, we can specify a Boolean filter there. And we can run this one again. We'll get the same output. You can see that this ends up being translated to a Boolean should query with our 2 match queries. And a Boolean filter there as well. So, yep, I briefly touched on covariant types. I have questions and answers within the same particular index in Elasticsearch here. So we can run a query here looking for C# async await within the body. And then all I'm doing is dumping out just the type that particular document has been deserialized to. So we have a bunch of answer types here and a bunch of question types. So that was kind of looking at text and looking at term queries and a couple of range queries. Now let's have a look at a geo query. So as well as all of the Stack Overflow data, I've also taken all of the Australian suburbs and I've indexed those into Elasticsearch. So we have the GeoJSON polygons for every single Australian suburb here. So let's have a look and see which suburb this conference is taking place in. Apparently we're in Woolloomooloo, which I don't think is true, but this is based on 2006 suburb data. So I've just done a geoshape point query here, specifying the geometry field, which contains the actual polygon or multi-polygon for a particular suburb. And I've just passed it the coordinates for this, for the Hilton Sydney. So we can see Woolloomooloo there. So taking that a little bit further, why don't we try and find the surrounding suburbs to Woolloomooloo? So again, we can use a geoquery here, and we can do an intersection. So let's grab the polygon for Woolloomooloo and tell me which other suburbs intersect with this given suburb. So we can actually go and grab the suburb. Let's get the coordinates from it, and then perform a geoshaped polygon and exclude this particular suburb as well. We don't want to get the original suburb that we're passing in back in the results. So we can run that one. We can see there's a bunch of GeoJSON here representing the polygon, and this is the start of our query. And then we can see here that Potts Point, Sydney, Darlinghurst are the intersecting suburbs with Woolloomooloo. Now, we don't need to go and grab the polygon. We can actually just say to Elasticsearch, hey, I want to find the intersecting polygons to a polygon that already exists in Elasticsearch. So use this ID and go and actually perform that intersection on Elasticsearch without me fetching it. So this will give you the same result here as well, just using the geoindex shape. And here, we're only returning the names of the suburbs here. We don't want the polygons for the suburbs coming back as well. We only want the names. So that's using fields there just to specify the name. So that was a kind of a brief tour of queries, geo queries, term queries. So let's have a brief look at aggregations. They kind of generally fall into three categories. Metrics, they can give you single numeric values or multi-numeric values. So stats, for example, give you the mean, median, average, standard deviation, variance, etc. Buckets is take a bunch of documents and put them into individual buckets based on some particular query or based on some aspect of each document. So there are ways of doing that to, say, specify, put questions into particular weeks in which they were asked based on their creation date. Or we may specify to put questions into buckets based on the tags that they've been tagged with. So there's a question about C#, question about PHP, etc. The nice thing with bucket aggregations, we can aggregate on those aggregations. So we can specify buckets and then specify buckets for those buckets and buckets for those buckets and n buckets deep. And pipeline aggregations there as well, those work on the output of other aggregations. So we'll see an example of these ones here. So let's start off simple. Let's just do a search using a max score aggregation. So find me the highest scoring question on Stack Overflow. So the highest score there is 14,772. And it's a question here about why is processing a sorted array faster than an unsorted array. So it's a question about Java. So that's great. So we've seen the max score. Excellent. Let's go a little bit further. Let's take questions and let's look at the top 5 tagged questions on Stack Overflow. And then for each of those top 5 tags, let's calculate some statistics for them. So mean, median, etc. And just simply dump those out in a table now so we can easily see those. So most questions about JavaScript. However, the highest scoring question, as we saw before, was actually Java. But if we look here, us C# guys, our questions are generally scored a little bit higher than both Java and JavaScript, so maybe we're asking slightly better questions. So that was an example of a bucket aggregation with another aggregation statistics on top of each one of those tags. Let's look at an even more complicated example here. So we're going to have a look at questions tagged DNX, .NET Core from 29th of June 2015. And then we're going to perform an aggregation on those questions that match our query. But we only want to look at DNX and .NET Core because questions can be tagged with more than one thing. But we only want to look at those two tags in this particular case. And then we're going to bucket those into weekly questions. And then on top of each one of those weekly buckets, we're going to perform a count of the number of questions there. And then on top of that count, we're going to do a moving average. So we're going to look at the moving average of those questions there using Holt Winters. And we're going to look at moving average window of 12 weeks. And we're going to have a look and see what that gives us. So we have it back in a table here. We can see the count, we can see the date, moving average, etc. But that's no good for us. We want to see it in a graph. So let's have a look in a graph. So what we can see here, for DNX questions, this peak here in this moving average is when beta 6 came out. We can see here, this is when RC1 was released. And then we can see these gradually kind of taper off a little bit, but we can see, boom, there's suddenly these .NET Core questions are just coming in. And this was when there was a move over from DNX to .NET Core tooling. One of the nice things with moving averages, we can also use it to predict where these things are going to go as well. So we can use that data to make a prediction. So let's see where things are going to go in the next 6 weeks. Okay. So yeah, DNX questions are going downhill. But we can see, hopefully, people getting more familiar with .NET Core. Questions are gradually sloping off. Nice thing with this moving average as well, it takes into account seasonality as well. So that was a brief look at aggregations. So let's have a look at autocompletion. So we're all kind of familiar with Google, of course we are. And if we want to do the same thing in Elasticsearch, we just simply do the SQL equivalent of where field like this thing. And as the data center burns, we walk away into the sunset. And we can do that as well if we want to in Elasticsearch by using a prefix, a wildcard, or a regex query. But that's kind of not the way to do it, really. You can do these are queries that exist, but they're more ad hoc rather than particular queries you want to use to solve a problem. There are usually better ways. So what better ways are there? There's something called a completion suggester. They are super, super fast. They are particularly designed for solving that search as you type scenario. So they use something called an FST, which is a finite state transducer, essentially a graph that maps out the relative paths from each letter within a particular string of characters. You can also apply weighting here as well. So use a weight from, so say, for example, if you're searching Stack Overflow for questions, you might want to weight those questions that have a higher score as being more important as you're searching. Term suggesters are a slightly different type of suggester. They allow you to provide things such as did you mean. So they're useful for spelling corrections. So given a set of terms, show me terms based on what exists within the corpus of documents. Show me terms that may indicate someone has slightly misspelled something. And phrase suggesters are really similar to term suggesters, except they take into account the entire phrase rather than individual terms. So we can have a quick look at those. So this is a regex query. We can see here the top example here doesn't start with WH as we expected, and that's because this field here has been analyzed, and therefore we are seeing a match here on when here on this particular token here. So we can see that quickly that we're falling down with this prefix query here. But if we have a look at using a completion suggester for that instead, we can see that we start getting some answers back, and we have a slight bit of fuzziness here as well, so it can take into account some spelling errors there. So, you know, so yeah, what the difference? So it's been able to understand that I've spelt things slightly incorrectly. So that's kind of completion suggesters. Term suggesters, Ruby on Rails, active recorder. Let's suggest some other terms for that. So for the Ruby term, for Ruby misspelt here, we're getting back the Ruby term here. This is the highest frequency, so we've probably misspelt this. For Rains, we can see here back that we're getting high frequency here for Rails, so probably misspelt as well. Active recorder, yeah, okay. Active records, maybe we might want to suggest that to the user instead. We might also use the result of this term suggester to feed into a query as well, to maybe cast a wider net. So that was kind of a brief look at term suggesters. So let's have a look at recommendations now. So looking at things, given this title, show me questions that may already answer the question that I'm about to ask. So what are shards in Elasticsearch? And we can take more like this. So given a piece of text or given an actual document, show me other documents that are like this document. And we can take that a step further with function scoring. So with more like this, we might also want to factor in other signals about the document. So our friends at Domain here, for example, they're able to, when you're looking at a given property, you might want to know about other properties that have similar attributes, such as beds, baths, parking, etc. But you may also want to weight those properties that are near the property that you're looking at higher than other ones, but then gradually degrade the weighting that you apply to those. And maybe properties that are newer, you might want to weight those slightly higher as well. That's what function scoring allows you to do. And significant terms is another type of approach that you can take to get recommendations for a given term, so for a given field of a document. So we'll have a very brief look at those things. So performing a more like this query, reduce shards in Elasticsearch. I'm typing out my question. That's my question title. We can go and have a look in Stack Overflow, reducing number of shards, how to improve. We can see a bunch of questions here around shards and Elasticsearch, which is what we would expect. So given a particular document, so the document that we were looking at last time, let's pass that in, use that to find other documents similar to this particular one. So we can see here, again, questions about Elasticsearch, kind of generally scored a little bit low. So let's see if we can improve this by using function scoring. So maybe we want to weight questions that have a high score higher than other questions. So we still want to find questions like the one that we're looking at, but then we also want to favor those that have a higher score, and we also want to favor those that are newer questions, because maybe Elasticsearch is changing quite quickly, so older questions may not be so relevant to things now. So we can use that to weight things, and if we have a look at the answers now, we can see we've got some much higher scoring questions coming out near the top here, and we've also weighted those as well that are slightly newer. So looking at significant terms, let's have a look at those users that have the C# badge, and let's look at other badges that users that have the C# badge also significantly tend to have. So some familiar kind of tags there. Those that answer C# questions, generally .NET, ASP.NET, Link. There's no kind of surprises there. That's just running significant terms on C#. Why don't we just have a look and see running it on those questions that are tagged C#, F#, and VB.NET. And now let's have a look at the significant terms for each one of those different badges. So if we run that, we find something kind of interesting here. So those that have C# badges, they're very much on the ASP.NET, MVC, SQL Server, JavaScript kind of train. Our VB.NET guys, they seem to be stuck in Visual Studio 2010, WinForms, yeah, maybe a little bit of C#4 cross-pollination there. And our F# guys, we're pattern matching, functional programming, OCaml, Haskelling away. So some very different badges there that we see. And we can use then significant terms as well to power graph exploration. I probably don't have time to go into that, but if you'd like to grab me afterwards, we can have a look through that stuff. But it's another API within Elasticsearch that essentially can use those significant terms to understand some implied relationships between values within particular fields in documents. So for example, we can look at the F# tag here. And we can see, as we saw before in significant terms, these are the badges that are most significantly related to the F# badge. So users having F# badges generally have functional programming, OCaml, Haskell, etc. And what we also receive back here are the relevant weightings for those particular badges. So how statistically significant is this badge related to this other badge? And we get the source badge here and the target badge, and we can actually use those then to form an actual graph. So within Kibana, so let's open up Kibana. We talked briefly about Kibana. We have a graph plugin. So we can kind of do the same thing that we saw in the API there. Let's have a look at users. Have a look at badges, F#. So this is using that graph API in the background, but it's just linking those badges up together there. So we can see there's a very strong relationship here between F# and functional programming based on the thickness of the connection there. And we can see that there's quite a large overlap there between those badges. One second, I've lost my slides. So that was a brief look at recommendations. And that was a very, very brief overview of a bunch of different functionality with Elasticsearch. Hopefully that was helpful to everyone. Do you have any questions? No, I obviously did a good job. Yes?
I'm currently working with a client who is very much into data warehousing, like your standard SQL with a large chain pumping data into and then generating reports out of that.
Yep.
How does Elasticsearch complement this sort of data warehouse traditional view of data?
We can talk about it afterwards because it's a very long answer. But it can complement it, yeah. But we'll chat afterwards. Thank you very much. And if you'd like to know a bit more about Elastic, here's the site and the GitHub repo for the client. Thank you.